my dear students. Welcome to India's biggest online platform, NE Educational Institutions. We can also draw stress versus strain diagram for different materials. From that, we can extract some properties of the material. Those are elasticity, ductility, and brittlity. Okay, these things we can explore from the stress versus strain diagram, comparison of these properties with the different materials. That part we can discuss in this particular session. Let's start the session. Stress versus strain diagram for mild steel, cast iron, and aluminium, here which are subjected under tensile loading. Tensile test is conducted for these three materials. Then you will be getting stress versus strain diagram. Now we can answer this question. Which material has greater value of Young's modulus? So procedure to judge which material is having highest Young's modulus from using theta values. See this curve, and theta ms is the angle made by mild steel curve about positive direction of x-axis, and theta cast iron, theta aluminium. Here you can write theta mild steel will be greater than theta cast iron and theta aluminium. Theta aluminium. You can apply tan here. Tan theta mild steel. Tan theta mild steel greater than tan theta cast iron. Tan theta aluminium. So what is the Young's modulus? Young's modulus, here Y is the Young's modulus. You can represent with E also. This is nothing but longitudinal stress by longitudinal strain, and the slope of the stress versus strain diagram. Stress versus strain diagram, that is nothing but tan theta. So this is equal to tan theta. So from here you can write Young's modulus of the mild steel greater than Young's modulus of the cast iron greater than Young's modulus of aluminium. Then higher the Young's modulus, higher will be the elastic behavior, or else here you can write it as, you can write Young's modulus as E also. Young's modulus, this would be Young's modulus of the cast iron, or else this Young's modulus of aluminium. Understood? So here you can confidently say Young's modulus of the mild steel. This is the Young's modulus of mild steel is higher. Young's modulus of mild steel is higher. Mild steel is greater or higher. Understood na? If you are interested to know the values, you can write it down. Young's modulus of mild steel equal to 210 gigapascal. Young's modulus of cast iron is 100 gigapascal. 100 gigapascal. Young's modulus of aluminium is 70 gigapascal. Okay, so here one important thing here is Young's modulus is the slope of the stress versus strain diagram. Stress versus strain diagram, that would be the slope. So for the line, here you will be getting slope. Slope is nothing but like this. Here you will be getting This is the stress and this would be the strain theta. Slope equal to sigma by epsilon. Here I can say tan theta equals to, here tan theta equals to sigma by epsilon, longitudinal stress by longitudinal strain. Understood na? It's very simple. You can easily calculate Young's modulus when the curve is given. Now I can say that, see this, from the Young's modulus, how to judge which one is more elastic. So here, so from here to here I can say, from here to here I can say that this is the elastic deformation. Elastic deformation of mild steel. This would be the elastic point and yield point of the material. So from here to here, this would be from here to here, from here to here, this may be elastic limit, and from here to here, this would be elastic deformation. I want to write this here to here. This is the elastic deformation of mild steel. Elastic deformation of cast iron. Elastic deformation of aluminium. So how to write elastic deformation? We already know Hooke's law. From Hooke's law only we'll be getting. So we know Young's modulus equal to E. From Hooke's law you will be getting this longitudinal stress. Longitudinal stress. Longitudinal stress by longitudinal strain. Here I can write longitudinal stress by longitudinal strain. Longitudinal strain. Longitudinal stress by longitudinal strain, sigma by epsilon. Here sigma equals to load by area of cross section. Epsilon equal to delta L by L. So finally E equals to force by area by delta L by L. So from here F L by A into delta L. So from here what is the elastic deformation? Delta L equals to F L by AE. Here delta L is inversely related with E. So here what is the elastic deformation? Elastic deformation of mild steel. Elastic deformation of mild steel. This would be delta L mild steel. I can say that elastic deformation of mild steel equals to F L by AE for mild steel. Understood na? So similarly you can write elastic deformation of, this is the elastic deformation of cast iron equal to delta L cast iron equals to F L by AE cast iron. So these all are some problems. You can directly take it. ठीक है ना? So here I can write elastic deformation of aluminium. Elastic deformation of aluminium. FL by AE aluminium. So you can write what is the load acting on aluminium specimen, length of the specimen, area of cross section, and Young's modulus. Here I can confidently write here Young's modulus of mild steel will be higher. Young's modulus of cast iron, Young's modulus of aluminium. Once you know Young's modulus of the material, you can easily calculate elastic deformation, del FL by AE. So this is the use of calculating axial deformation. This is the use of Young's modulus in order to calculate axial deformation. So this is up to elastic limit. You can axial deformation up to elastic limit is called elastic deformation. From that content, we will be discussing elastic behavior of the material. Which one is more elastic? You can easily say which one is having highest elastic property of the material. So just now we had a discussion. Here it is what Young's, from Young's modulus only we will be discussing. Young's modulus of the material is greater than Young's modulus of cast iron, greater than Young's modulus of aluminium. And one more thing, this is what I want to write again. I want to write this again. From here to here, the deformation up to elastic limit. The deformation up to elastic limit is called elastic deformation of the material. The deformation up to elastic limit is called elastic deformation of the material. Higher the Young's modulus, lesser will be the elastic deformation of the material. So higher the Young's modulus, lesser will be the elastic deformation of the material. This would be elastic deformation of mild steel, elastic deformation of cast iron, elastic deformation of aluminium, elastic deformation of aluminium. The deformation up to elastic limit, elastic deformation of the material. Deformation is nothing but the deformation up to axial deformation up to elastic limit. I can say that axial deformation up to elastic limit. Axial deformation up to elastic limit. Okay na? So you can write it as delta L. Delta L equals to FL by AE. FL by AE. So I can say that delta L is inversely related with E. Higher the Young's modulus, lesser will be the elastic deformation. So you can say delta L mild steel. This is the delta L mild steel less than the delta L cast iron. Delta L cast iron less than the delta L aluminium. This condition is valid when F by F L by E. equal to constant. FL by A is constant. Same load is applied on 3 specimen. Length of the 3 specimens same, and area of cross section of the mild steel, cast iron and aluminum same. In that case, delta L you can directly write like this. Understood now? So here elastic deformation. Here I can say that elastic deformation, elastic deformation, elastic deformation of the mild steel less than elastic deformation, deformation in the elastic region less than the elastic deformation of aluminum. So lesser the elastic deformation, higher will be the elastic property of the material. Here lesser the elastic deformation, higher will be the elastic property of the material. So lesser the elastic deformation, lesser the elastic deformation, lesser the elastic deformation, then higher will be the elastic property of the material, higher the elastic property of the material, elastic property of the material, property of the material. Understood na? So delta L is less, it can easily, so lesser the elastic deformation, it can easily come back to its original position. So lesser the delta L, then it can easily come back to its, original position. That is the elastic property of the material. So what is the elastic property of the material? What is the elastic property? Here I can say that. So it can easily come back to its original position. It can easily come back to its original position. Come back to its original position. So that is why that is the elastic property of the material. So here I want to rub this. See here, we already know that Young's modulus of mild steel greater than Young's modulus of cast iron greater than Young's modulus of aluminum. So elasticity is the property of a material and ability to come back to its original position. Ability of the material regain back to its original position. Okay, now regain back in the sense come back to original position. So that is the delta L is less. Then it can easily regain back to its original position. So that is the thing. Okay, so elastic deformation you have written like this. From this is the data. So which material is having highest? So from here, highest elastic property of the material is nothing but mild steel. Mild steel. Understood na? Mild steel is having highest elastic property. Now, we can have a look on the, see this, which is having more ductile. It is very simple. So what is the ductile property? It is the property of a material. It is ability of the material to deform plastically under tensile loading, which is having higher plastic deformation, then it is more ductile. Okay, na? So deformation in the plastic region. It is very simple to write. Here it is having from here to here. This is the plastic deformation. Plastic deformation. Deformation in the plastic region. This is the deformation in plastic region. So here it may be yield point. Yielding is here. From here to here, this is the deformation in plastic region. It is very less, very less. There is no very less. Okay. Okay, so it's a brittle fracture. Okay, so it's a brittle material and brittle fracture. So that is the very less. Plastic deformation is very less. So from here to here, I can say plastic deformation in the aluminum. Here this would be, this is the plastic deformation of mild steel. So I think almost negligible. Okay, plastic deformation of cast iron. So this is the deformation, plastic deformation of aluminum, considerable. Plastic deformation of, this is the plastic deformation of mild steel. Here I can say that this would be plastic deformation of, this is the mild steel. So considerable, it is very negligible. Okay, cast iron is very negligible. So I can confidently say that higher the plastic deformation, then higher will be the ductile property. So plastic deformation, you can say plastic deformation is nothing but deformation of the material in plastic region. Higher the deformation of the material in plastic region, then it is more ductile. So you can say that this is the plastic deformation. Deformation in the plastic region. Deformation of the material in plastic region. Deformation of the material. Deformation of the material in plastic region. Material in plastic region is nothing but plastic deformation. So from the diagram you can easily say that plastic deformation of the mild steel will be higher than the plastic deformation of aluminum is higher than the plastic deformation of cast iron. Okay, so it is the, I think this is the yield point of the, this is the yield point, this is the yield point, I can say yield point, yield point, from yield point to brittle. Okay, this is the breaking point. That is the, I think sudden failure will occur. There is no reasonable plastic deformation of the cast iron. That is why cast iron is a brittle material. Sudden failure will occur. Brittle material. This is the brittle material. So this is the ductile material. Ductile material. Ductile material. Aluminium is also ductile material. It is also ductile material. Okay, so plastic deformation is very less. Okay, na? So almost negligible. So that is why here this would be plastic deformation. Higher the plastic deformation, higher will be the ductility. Higher the plastic deformation, higher the plastic deformation, plastic deformation, higher the plastic deformation, higher the ductility, higher the ductility. So which one is more ductile? Tell me, which one is more ductile? Mild steel. Mild steel. Understood na? Which one is more ductile? So we can say this is mild steel. Understood na? So plastic deformation is higher in case of mild steel. Deformation is higher in plastic region. So more plastic region it is having. So then you can call it as higher the plastic deformation. Then only we can call it as more ductile. In this manner we can decide which one is more ductile. Now we can see that which one is stronger material. Stronger material, it is very simple to say. It is very simple to say. I am taking one point here. I am taking one point here and draw like this. This would be, I am taking like this. Which one is more stronger? It is very simple to say. Here I am taking like this. So for corresponding deformation or strain, for corresponding strain, okay na, at a particular value of deformation, for particular value of deformation, anyhow original length will be same. For particular value of deformation, so sigma aluminum, this would be sigma aluminum, sigma cast iron, and here somewhere sigma mild steel will be getting. So here it is nothing but, from here to here I will be taking. So corresponding values, this and this. Understood na? So these are the values. Here sigma mild steel is higher than the, here I can say sigma mild steel will be higher than the, for constant strain, for a particular value of strain, for given strain, for a given axial deformation, okay na, the stresses induced in the, the stresses induced what are the stresses induced? Sigma mild steel will be greater than sigma cast iron greater than sigma aluminum. Okay, the more amount of stresses induced in the mild steel, even though it is able to withstand that much amount of stresses without occurring any failure. That is why mild steel is more stronger than cast iron and aluminum. Okay, so from that you can easily give this statement. Here mild steel is able to mild steel specimen is able to withstand more stresses for given strain, okay, for given strain. That is why mild steel is more stronger than cast iron and aluminum. You can easily say that. So one more way is, here this is the yield point and this would be yield point. Here somewhere yielding will be here. So in order to judge which one is more stronger, from here to here, this is the yield strength of cast iron and yield strength of the cast iron and yield strength of the Yield strength of the aluminum. Yield strength of the mild steel. Yield strength of the cast iron. Yield strength of the aluminum. Okay, so based on the yield strength also we can decide. This is the yield strength of the mild steel. Here it is yield strength of the cast iron. Yield strength of the aluminum. Yield strength of the aluminum. So I can say that here yield strength of the mild steel. Yield strength of the mild steel is higher than the yield strength of the cast iron, yield strength of the aluminum. So here which one is more stronger? Which one is more stronger? This would be more stronger for given value of deformation. This is the forgiven value of deformation. So mild steel is more stronger. Mild steel is mild steel has highest strength. Highest strength. Okay, so for given deformation, so mild steel is able to withstand more loads. Okay, so then it is more stronger. Now, so we can say that which one is more brittle. Okay, so brittleness, it is nothing but which is having lesser plastic deformation, the sudden failure will occur. Lesser the plastic deformation, higher will be the brittleness. Understood na? Higher the plastic deformation, higher will be the ductile property of the material. Higher the plastic deformation, higher will be the ductile property of a material. Lesser the plastic deformation in the sense sudden failure. Understood na? Then it is more brittle. Okay, so lesser the plastic deformation, then higher will be the brittleness of the material. Okay, so here I can say that sudden failure will occur. In this case, failure, this is the sudden failure is observed. Here brittleness means sudden failure at the fracture point. Sudden failure will occur in brittle materials. Sudden failure. Okay na? Sudden failure will occur. Sudden failure occurs at the fracture. Those materials are called brittle materials. So sudden failure in the sense lesser the plastic deformation. So very less. So here it is nothing but this would be brittle material. This is brittle material. Brittle material. Okay. Sudden failure. This is the ductile material. It is not sudden failure. Ductile material. Okay, so it is not going to, here cast iron is not going to plastic region. Suddenly it will fail. Okay na? So for example, chalk piece, once you apply the load on chalk piece, it will fail suddenly. It will fail suddenly. Understood na? That is the brittle failure, brittle fracture. Material is brittle material. Okay, so lesser the plastic deformation, it is not going to plastic region. That is why plastic deformation is very, very less. Understood na? So here I can say we already know that plastic deformation of mild steel is higher than the plastic deformation of cast iron, greater than the plastic deformation of, this is what, aluminum, far greater than the, this is cast iron. So it is not going into the plastic region. So that is why it is very less. Plastic deformation is very, very less. Lesser the plastic deformation, then it is more brittle. Lesser the plastic deformation, then it is more brittle. More brittle. Understood na? Which one is more brittle? Tell me. Cast iron. Cast iron is more brittle. Okay na? This is the brittle material. Please do subscribe METube Intel Physics YouTube channel. Thank you. We can meet in the next class. Thank you.